We have learned the importance of intellectual property protection and the basics of digital watermarking. Now we will show a couple of examples to see how to embed digital watermarks into hardware design intellectual properties. The first example is on Boolean expression optimization. The problem is to rewrite a Boolean formula with don't care conditions using the minimum number of literals. Our goal is to protect the minimized formula, which is the design intellectual property in this case. The approach we use is to embed one bit of information behind each don't care conditions. When we want to hide a bit 1, we force the don't care condition to be 1. And when we want to hide a bit 0, we force the formula to be 0 on the don't care condition. For example, to hide the message 01, we make the first don't care condition to be 0 and the second don't care condition and that condition, the formula will be evaluated at 1. And thus, the formula becomes this new form, which has one additional term, A, B, C, D, corresponds to the second don't care condition. And we can find the optimal solution in this case, which F becomes A prime, B, C prime plus BD. And similarly, to hide the message 10, we can include the first don't care condition into the Boolean formula, and then leave the second don't care condition away. So this is because the second bit is 0. And as a result, we obtain this solution, which is distinct or different from the first one. To summarize this example, we see that we can hide watermark by specifying values to don't care conditions. In this example, any 2-bit message can be embedded and we will get distinct watermarked solutions as shown here when we add either 00, 01, 10, or 11, and we get 4 completely different solutions. However, we see some of these solutions are better than others. For example, the solution with 01 and 11 as watermark, they both have 5 literals as the solution. And however, the other 2 have 9 literals. This is one of the challenges for watermarking, which is known as fairness, and we will talk about this later. Let's see another example. This example is a radix 4 to binary encoder. What we have here is, this is the truth table, where we have each of the 4 symbols in radix 4 number system, and we will convert each of these symbols into a binary representation with 2 bits. And we know that the input has 4 bits, and so we have 2 to the power 4, 16 different input combinations. However, the truth table has only 4 of them. That means there are a total of 12 don't care conditions. And we listed them there numerically, start from bit 0000 all the way to 1111. And output in all these cases are don't cares, which are represented by this double cross. And assume that we want to add a 2-digit letter, DA, as our watermark. DA stands for design automation in this case. The first thing we do is we represent these 2 letters into binary information. And what we do is we consider their ASCII code D and A. And then we also add a parity bit at the end. So this gives us a 15-bit watermark. And to embed this 15-bit watermark into the original truth table or the original design, what we do here is we see there are 12 don't care conditions. With 12 don't care conditions, we can embed 3 bits. This is because if we want to embed 4 bits, we may end up with the situation that it does not exist in these 12 don't care conditions, because 12 can represent 8 different combinations of 3 bits, but not 4 bits. So what we do is we consider the last 3 bits of the watermark, which is 0, 1, 0, which is a binary 2. So what we do is we come to our list of don't care conditions. We see 0, 1, and 2. So this is the don't care condition. We are going to specify a deterministic value to embed our signature. And what value should the system output in this don't care condition? That depends on what is the message you want to embed here. So what we see in the original watermark, the next 2 bits, which because our output has 2 bits. So the next 2 bits are 0, 0. So that is why I replace these don't cares by 2 zeros. And similarly, I can move on to the next 3 bits. I can do this because now the don't care table has 11 don't cares. I can still do 3 bits. So this 3 bit is 1, 0, 0, which is the binary 4. So what I do is I count 0, 1, 2, 3, 4. So this is the don't care condition. I'm going to force a value. And the value happens to, again, to be 0, 0, because the next 2 bits in the watermark are 0, zeros. And then we keep on this process, and the next 3 bits are 0, 0, 1, which is the binary 1, so 0, 1, and then the message we want to add are the leading bits, which are 1, 0. So now we have successfully converted this 15-bit watermark into 3 pairs of input and output, and we added them into the original truth table, and then we got an augmented truth table, which we called the watermarked truth table. Now we will show how design will be conducted with the original truth table and the watermarked truth table. So from here, we can easily see that the 2 outputs, X and Y, can be represented by C plus D and B plus D, or simply 2 OR gate. And however, to implement the watermarked truth table, the expression becomes a little bit more complicated. So in this case, instead of 4 literals, 2 logical gates, we need 1, 2, 3, 4, 5, 6, 7, 8 literals. This is something we know called a design overhead. And again, we'll discuss about the design overhead later. The final example is on a combinatorial problem that has a lot of applications in hardware design and optimization. The problem is known as graph vertex coloring problem. So what we have in this problem is we have an undirected graph, and we want to color the graph by giving each vertex or each node a color, such that whenever 2 nodes are connected, we must give them different colors. For example, node B and node D, they are connected. So B and D, they have to receive different colors. So this is one of the sample solutions here. We see, A, B, C, D, they all get different colors. And then H has the same color with D because they are not connected. And H has to have a different color with G because they are connected. And you'll see this problem is not that hard to solve, but what is harder is when we try to minimize the number of colors we need. As a matter of fact, if we consider whether a graph can be colored by 2 colors or not, which is known as the two-colorable problem, that problem is trivial to solve. However, when I ask you whether a graph can be colored by 3 colors or not, the 3-colorable problem turns to be NP-complete. And in fact, the 3-colorable problem is one of the most important NP-complete problems. And it has a lot of applications, in particular for digital VLSI design. Now we will show how we can embed watermark into a solution to graph coloring problem. So what we have here is we have a graph with 11 nodes and probably around 20 edges. What we want to do here is we want to protect our solution to a coloring scheme of this graph. And what we do is by hiding a message 2000 into the solution to achieve such protection. The first thing we do, as we showed previously, we need to convert our signature or our message into binary. In this case, the decimal number 2000 will be converted into binary bit sequence here. And what I do now is I want to show you step by step how I can hide this bit stream into the graph, and then solve the graph, find the solution. The first thing I do is I take a look of node 0. I want to find the next two nodes that are not connected to node 0. In this case, I see 0 and 1, they are connected, so 1 is not a candidate. But both node 2 and 3, they are not connected to node 0. So 2 and 3 will be candidates in this case. And to hide a bit of information, what I'll do is I'm going to add one additional edge starting from 0. And what is the receiving end or the receiving node of this edge? That depends on the bit I'm going to embed. So if I want to embed a 1, I'm going to connect a 0 to 3. If I'm going to embed a 0, I'm going to connect a 0 and a 2. In this case, because I want to embed a 1, so what I do is I connect a 0 and a 3. And similarly, I move on to the next one, node 1, 3 and 4, they are the next two nodes that are not connected to 1. And to add another bit 1, I connected 1 and 4. So I can repeat this process, and at the end, all these 11 bits will be embedded into this new graph, which we call a watermarked graph. And these are the dotted edges correspond to the bit 1, 1, 1, and so on. So now I use my tool or find out a smart way to color this graph. And the solution I get is, this is one of the examples. And we see it requires 0, 1, 2, 3, so altogether 4 different colors. And in this solution, we noticed some interesting things. So for example, node 8 and node 7, they receive different colors. However, this is not required in the original graph. As a matter of fact, indeed, I can also put node 8 as blue, which also satisfies all the requirements, which means that for all the nodes that are connected to 8, they're not in the same color in the original graph, but not in the watermarked graph. So the fact that this solution satisfies a set of additional constraints will be used as the proof of our authorship.